Hello, everyone. Welcome to Research Tips. I am Sushma, an epidemiologist and researcher with more than 10 years of experience. On this channel, I focus on step-by-step tutorials and research tips to help make your research journey easier. In today's video, we will learn about difference and differences, also called DID, which is one of the useful techniques to estimate causal effect in quasi-experimental design in any areas, be it public health, economics, business, banking, etc. So in this tutorial, we will estimate the same causal effect in four different ways. Each approach adds another layer of understanding, but all of them arrive at the same answer. So the first approach is arithmetic intuition. And here we begin with simple arithmetics and then compute the DID estimates directly from the raw observation. Second is the counterfactual reasoning. Here we calculate the estimate based on the value of what would have happened to the intervention group if they had not received any intervention. And this is the concept of counterfactual. And thirdly, we will derive the same estimate from a regression model by solving the coefficients manually with our hands. And I believe this section will be helpful in deepening the understanding of not only the DID concept, but also the concept of any linear regression model. And finally, we will confirm the results that we receive from these three approaches using a statistical software. So for the purpose of this video, we will use RStudio to fit the model and then get the estimates and the uncertainty, 95% confidence interval. And the interesting part is, although each approach look different, they all lead to the same causal effect, same estimate. So whether you later use a simple difference in difference model, a two-way fixed effect model with multiple time periods, or other more advanced differences approach, they all build on the core concept that we will cover in this tutorial. So ready for this? Let's get started. So first, let's look into our data. And if you want to do it side by side or want to do it later, I have posted the link to this data in the video description. So the context is we have two districts, District A and District B. And we have data on maternal mortality ratio, MMR, per 100,000 live births for these two districts for the year 2000 and for the year 2003. So there was a intervention called, this is hypothetical, okay? So suppose there was an intervention called maternal health initiative intervention that was implemented in the year 2000 in district A, but not in district B. But these two district A and B are similar in different background variables. For example, the sociodemographics or economic status or other indicators that might affect the health policies, right? So they are similar, but one district receives this specific intervention in the year 2000 and the other does not. So the maternal mortality ratio in year 2000 in District A is 400 and in District B is 310. And in 2003, the MMR in District A, the intervention district, is 370. And in District B, the comparison district, is 289. So here, year 2003 is the post-intervention period and year 2000 is the pre-intervention year. So when we see the data of these two districts in the post-intervention year, we see that the crude difference in MMR between these two districts is 81. So 370 when we do 370 for intervention district and 289 for the control district. When we subtract them, the crude difference is 81. So that means district B that didn't receive intervention has the lower MMR. So MMR, if that's lower, that's good, right? So just looking into the post-intervention data, we see that the MMR in the intervention district is greater than the MMR in the comparison district. So does this mean the intervention did not work as expected? Why is the rate still higher in intervention district? It should have been lower, right? So that is a question. But there is something that we need to be careful of is we are just doing the difference in the data from post-intervention time. And here we do not actually think about the differences in these two districts during the pre-intervention time, right? We said these districts are similar, but they are not identical, right? So we have to take into account for that difference between these two districts that they had during the pre-intervention time. So first, let's see the first approach. And here we get the DID estimate represented here as the as delta DD. And here we take the difference of the differences in MMR for each of the district before and after intervention. So here what we did is we took the difference in MMR in district A after and before getting treatment, and then we subtracted from that the difference in MMR in district B after and before the intervention. So so that is the difference in differences, and here and the name DID. And this -9 that we get from taking the difference in these two differences can also be obtained by taking the difference in the rate for the two district after intervention and before intervention. So here we see that we did MMR in district A post-intervention minus MMR in district B post-intervention, and then we subtracted from that MMR in district A pre-intervention and MMR district B pre-intervention. And the resulting estimate is again the same, it's -9. And what does this -9 mean is the MMR decreased by additional 9 deaths per 100,000 live births in the intervention district compared to the decrease that was observed in the comparison district. So let's clear the first approach. So coming to the second approach, the counterfactual reasoning, it tries to answer the situation that is counterfactual, which means what would have been the value of MMR in District A in the year 2003 if the district had not received any intervention. In reality, we would never know exactly the counterfactual situation, right? To know that, we would have to do the time travel, go back in time, and do everything exactly the same way except the intervention. But that's not possible, right? So here we try to answer that question, assuming that if District A had not received the intervention, it would have followed the trend just like District B. Because remember earlier we said that District A and District B are comparable in many different indicators. And this is an important assumption called parallel trend assumption in DID analysis. So here, the slope of this red line, the comparison district, can be calculated by simple slope formula, rise over run. That is the change in vertical distance divided by change in horizontal distance, or in other way, y2 minus y1 divided by x2 minus x1. If we do that, we can easily get it 289 minus 310 divided by 1 is the slope of the red line, which is -21. And then we assume that the slope of both the red and green line is same. So that means if the slope of this green line was -21, we can then easily calculate the change in horizontal distance. Y2 is equal to 400 minus 21. We can do that, and we get 379 is the value of MMR for District A in 2003 if it had not received the intervention, assuming that the trend for this district would be same as the District B. And once we know this value 379, we can get the causal effect of the intervention as the difference of what happened and what would have happened, 370 minus 379 minus 9 as the causal effect, delta dt, that we calculated earlier. So it also matched, right? So let's clear the approach 1 and approach 2. Now let's go to approach 3. So coming to the third approach, for this we have to reformat our data by adding dummy variables. So the first dummy variable we add is treat, which is coded as 1 if the district received the treatment and coded as 0 if the district did not receive the treatment. And the other dummy variable we add is time. So it would be coded as 1 if it is the post-intervention time, and it will be coded as 0 if it is the pre-intervention time. And then lastly, the third dummy variable is the interaction of this time and treat variable. So we can calculate it simply by multiplying the treat and time. So for the first observation, treat is 1 and time is 0. So 1 times 0 is 0. So, and the last column is the outcome, MMR. So you can keep the MMR, the outcome variable, anywhere, but in the data we need to have these 3 additional dummy variables. So our regression equation is of this form: y dt, that is the MMR for district D in time t, is equal to beta naught, that is the intercept, and beta 1 times treat variable, beta 2 times time variable, and beta 3 times treat and time interaction. So this beta 3 is our measure of interest that gives the causal effect that we have been calculating or are interested in. So here, if, for example, if we would write this equation for the first observation, district A, it would look like 400 is equal to beta naught times 1 plus beta 1 times 1, that is the value of treat, beta 2 times 0, that is the value of time, and beta 3 times 0. So here in this, from this table, we bring in the value of this treat and time, the predictor variables. So, and then there is the error term, of course. So imagine if we have 1,000 observations, then we will have 1,000 similar equations. But thankfully, we can represent all these values of predictors for each observation using a single design matrix. So the design matrix looks like this. So the first column of this matrix is for the beta naught. So we keep 1 for the intercept value. For example, here beta naught multiplied by 1, right? And then the second column of this matrix is for the variable predictor treat, the dummy variable treat. And then the third is for time, and the fourth is for treat multiplied by time. So the next step is, since we are trying to minimize the sum of squared residuals via ordinary least square regression, we multiply this matrix X by its 1 transpose. So we get the transpose by converting this first column into first row, and then second column into second row, and so on. Here you can see, and then we multiply these two, transpose and then the X. So when we do that, we get this matrix 4, 2, 2, 1, 2, 2, 1, 1. So how you can do it is we multiply the first row of this transpose with the first column, each value corresponding value of the first column in the X matrix. So that means, for example, 1 times 1, 1 times 1, 1 times 1, and then 1 times 1 for the first cell, first row, first column cell of this multiplied matrix. And then for the second, we multiply the first row of this transpose matrix with the second column, each cell in the second column of the X matrix. And doing that, we get this. Then we compute the product of X transpose and Y, where we multiply the values in the rows by rows of X transpose with the values in the Y matrix. For example, for the first row in X transpose, we multiply 400 times 1, then 300 times 1, then 310 times 1, and then 289 times 1, and so on. And then we get this value here. Now we have all the values that we need to fit this equation. Product of X transpose times X multiplied by beta is equal to product of X transpose times Y. So we have the matrix beta, X transpose times X, and then X transpose times Y. So when we fit these values in this equation, we get these four different equations. So from these four equations, we can now easily calculate the values of beta naught, beta 1, beta 2, and beta 3, our coefficients, right? So finally, what we calculate is beta naught is equal to 310, beta 1 is equal to 90, beta 2 is equal to minus 21, and beta 3, that is the estimate or coefficient of our interest, the causal effect. Is minus 9. So this value is same as the value that we obtained from the earlier two approaches. So, and excuse my handwriting, it's a bit messy. So that was a lot, but we did it. Clear this third approach also. Now we have the fourth approach, DID, using statistical software, and it's the relatively easy one. So we will go to the R Studio to do that. So let's go. So here in my R Studio window, we can see that there are two data sets. Let's first go to the first data set, book 2. So let me open it. You can see here that there are four observations, district A and district B. And then it's the same data that we have been seeing earlier, right? So there are four data points for two districts. And let me read this data is the data frame, and then let's run this model, model 1 linear model, where the MMR is the outcome, and then we have treatment and time. Uh, and then when we run this and then see the summary, we see that we have this coefficients there. We have intercept of 310. It's the same intercept that we calculated earlier. And then the coefficient of treatment is 90. Coefficient of time variable is 21, and the interaction of treatment and time is minus 9. This all of these four value match. But here we see that the model is not able to give us the value of standard error and the p-values and uncertainties, right? So the reason behind that is because we have four data point, four observation, and we have four parameters to estimate. The first one is beta naught, then beta 1, beta 2, and beta 3. So four observation and four parameters. That's why the degree of freedom is 0. That is why it's not able to calculate the uncertainty, because so if we have more data point, then we can get these other estimates. So I have created this another book 3 here by adding some more data points and for the two districts post intervention. And when we fit this model, model 2, the same way that we did earlier, and see the summary, we can see that there we get the standard error and the p-value estimates also. And so here now we see that the value is 61. It's different because earlier we calculated using for only four observations, but now there are total of 12 observation, so the value is different. But the point that I wanted to make here was for just the four observation, we will not get the uncertainty estimates. And we need more data points to get that, just like we saw here. So here, let's go back and try to make sense of this -9 estimate that we have been saying is the coefficient of our interest. The how we can interpret this value is intervention district has an additional 9 maternal mortality per 100,000 live births prevented, controlling for of the baseline difference between these two districts and the common time trend for this two district. So that way we can interpret the value. So that is all. It's very simple when we do it using the software after we have gone through all those different steps. I hope this tutorial helped you in gaining deeper understanding about the concept of difference and differences estimator. This conceptual foundation will make it much easier to understand more advanced DID methods. Thank you for watching.